So when we were talking about instantaneous rate of change, we talked about this idea of being at an instant or being like infinitely close to a point. Or we could talk about what's happening as we approach that point. And all of that terminology of being like infinitely close and approaching is the idea of limits. What is the limit of our function as we approach a certain value? So where we're going to start is with a two-sided limit. This is where we approach from both sides. So our notation here, so LIM is standing for the limit. And then we have this subscript here. So it's x with an arrow to a. What we're saying there is this is the limit as x approaches a. And we'll talk about one-sided limits a bit later on, but I'm just going to throw in parentheses that x approaches a from both sides. So x approaches a is coming from that subscript of x with the arrow to a, and then what we're applying this limit to is f of x, so our function. So this is the limit as x approaches a of our function f of x, and then what we can see is that it's equaling some letter L, so we're just going to say is L. So all that notation there with LIM, x arrow a, f of x equals L, how I would read that out loud is the limit as x approaches a from both sides of f of x is L. So what does that mean? So what I'm going to do is draw some pictures for us because we have some different scenarios. But the idea is if we have some function f of x, and what we're doing is we're looking at some point a, so some value for x that's equal to a. So if we're at a, there's going to be some point on our function where that's occurring. And how I drew this graph currently is that we're defined at that part of our function. I'll talk about what happens if we're undefined. So this idea of a limit, so x approaching a from both sides, it's this zoomed in idea. So if I get really close to that coordinate, what this would be the coordinate a, f of a, let's just say this is where x is equal to a, because we're going to change up that notation in a bit. But what we're doing is it's like we're walking along our function. So what we can do is approach from the left-hand side. So it's like I'm walking along the function, approaching this point from the left. And at the same time, I'm thinking about what happens as we approach from the right too. And what's happening is we're closing in on this coordinate. In this case, since we're defined, we're closing in on this coordinate a, f of a, so that output. So what we're interested in is like if we're coming to the left, we're getting closer and closer to that coordinate. And we specifically want to know what's happening to the y values. What are the y values approaching? And same thing from the right-hand side. What are the y values approaching? And what would happen here is this y value that we end up with, that we're approaching from the left and the right, that would be our value L. So L, that limit, is representing the y coordinate of that value that we're approaching from the left and right. In this case, it would be exactly equal to f of a. It would just be our function output because we're defined there. What we're going to see is sometimes we're undefined at this point. So I'm going to draw a similar graph, but let's say there's a hole in the graph. Let's say we have something like this, and that value a that we're interested in approaching with x, let's say that's occurring right at that where that hole is. So approaching from the left, approaching from the right. This is why we use the word approaching. It isn't just evaluating what's happening at that point because we still have a limit here. Because the idea is that in terms of y values, we're getting closer and closer and closer to this spot where the hole is occurring. And same thing from the right-hand side, we're getting closer and closer and closer to that y value that's occurring at that hole. So even though we're undefined there, the limit still exists because we're approaching this value. So it's all about getting closer and closer from both the left and right. So in this case, that y value where the hole is occurring, that would be our value for L. That would be the value of the limit, because it's what's happening to our function as x approaches a from both sides. And if I did something like, let's say we were defined at a, but just somewhere different. So I'm going to have this kind of separated coordinate, let's say down below where the hole is, our limit doesn't change. So this is called a removable discontinuity. A very formal way of saying is just a point that's defined separately from our graph. But the idea of limit is the whole idea of what's y doing as we approach this value. In terms of approaching, we're getting closer and closer to where that hole is occurring. It's not connected to that separated point at all. So this is the idea of our two-sided limit. It's looking at what are the y values approaching from both the left and right-hand side at some x value of a. So let's take a look at this with a function. So we have a rational function here, x minus 4 over x squared minus 7x plus 12. And what I'm going to do is I'm going to show you how to use your Desmos calculator to help fill in a table like this where you have a bunch of different x values, and we can do it rather quickly. So what we're going to do is evaluate for these values 3.5 through 4.5. And as you can see, what we're doing is in here is the x value of 4, but we're skipping over it. And it's because 4 is going to be undefined. So I can even put that onto our table when we build this. Okay, so let's talk about going to Desmos. So we're going to do the graphing calculator. And really I'm going to focus on this left-hand side part because I provided the graph down below there so you can see our rational function and how there's a hole right at 4. So we want to see what's happening to these y values as we get closer and closer. Now visually we can see they're getting closer and closer to 1, but let's see how we can evaluate that numerically with this table right here. So what we can do is in the Desmos graphing calculator, above where we typically write in our function, we have this little plus symbol that stands for add item. And what we can do is create a table. So if I create a table, it's going to have an x1 side and a y1 side. So what we want to do is define the relationship between x1 and y1. So I'm going to do is for the expression below the table, so for expression 2, I'm going to type in our function that's up above here. So what I'm going to do is instead of f of x, I'm going to use y1. So I'm just going to do y1. And when I typed that in, I didn't do anything special to make it be a subscript. It just automatically did that. So I just typed y1 and then equals, and then we're going to separate up and we want to do x1 minus 4. So x1 minus 4. And then down below, x1 squared minus 7x1 plus 12. Sorry about that. So I'm going to go back on those instructions I just gave because I was getting an error out, and there's a better way to do it. So, okay, going back a little bit, adding that table so it has the x1, y1, what I'm going to do is edit it. So instead of x1, I'm just going to call it x. And then instead of y1, what I'm going to do is type in the function. So I'm going to separate up my fraction. In the numerator, I'll have x minus 4. In the denominator, x squared minus 7x plus 12. So all of that in the table there is just at the kind of column titles. We have x and then our function. Now what we can do is under x, we can just start typing in our values. So like 3.5, 3.75, 3.9, 3.99, 3.999, 4.001, 4.01. So this is just a nice way to get quick calculations using our table. So, and then actually you can see on the right-hand side here, it's graphing those separated coordinates. So you can see how it's mapping all those values that we're typing in. So again, it was the addition button that's for add new item, and then you just adjust the titles of the columns so you have X and then your actual function involving X. So you don't need to worry about the X1, Y1 at all. And then you just type in your X values, and then that second column we get the list of values. So what I'm going to do is start copying those down. So for 3.5 we had 2. 3.75, we had a 1.33, 1.11, 1.01, 1.001. So as we were approaching, would be from the left-hand side, we're getting closer and closer to 1. And then if we get to where X is 4.001, there will be at 0.999. Here we have 0.99, 0.91. So we're getting further away from our y equals 1 here, but the idea of approaching from the right-hand side, we would actually be reading up the table. So we would still be approaching this idea that 1 would be the value that's occurring between that value for 3.99 and 4.001. Our output is 1 in between those two values, where our function itself is undefined, but approaching from both sides, what we can see is I would write this as the limit as X approaches 4 of our function f of X is equal to, and that limit would be equal to 1. So it's the Y value that's, in this case, missing from our functions, what we're approaching from both sides. And again, we can see that with the graph itself, where we have this hole right here at 4, 1. It's that would be our limit is at y equals 1, because that's the Y value we're approaching from the left and the right. So then what if we added a separated coordinate at 4, -5? So I'm going to do is plot the point 4, -5. So now we are defined at X equals 4. So like if I was making my table, I could include 4, and instead of it being undefined there, I would have an output at -5. But again, the idea of limit, the limit wouldn't change at all, because it's this idea of approaching. It's what's happening from the left-hand side and the right-hand side. It's not necessarily what's happening exactly at that X equals 4. The idea of limit is this idea of getting closer and closer. So what if we added a coordinate defined at 4, -5? The limit does not change. It would stay the same because we're still approaching that positive 1 from both sides, even though we're defined somewhere else. All right, so let's take a look at a few more examples here with this idea of a two-sided limit. So for this first example, we have a graph. So you have this kind of polynomial here that goes down. We hit 0, 1. We're defined at 1, 2. We go up to this kind of peak, but it's a hole at 2, 3. We go down to 3, 2. And there's this removable discontinuity, that separated coordinate there at 3, 2.5. And then what we have is we go up to a hole up at 4, 3.5. And then we have this jump. So then there's a hole at 4, 1. So we have this jump here that usually comes from our piecewise functions. And then we just have a constant function of y equals 1 as we go to the right there. So let's talk about evaluating these different limits. So the first one, let's look at the limit as X approaches 1. So X approaches 1, we are actually defined there. So if we're defined at that coordinate, the limit is just going to be equal to that Y value. So in this case, we have the coordinate 1, 2 is defined. So if I'm evaluating that limit as X approaches 1 of f of X, the limit would be that Y coordinate of 2. If we have a hole, it's just a little different because we aren't actually defined there. We don't have a coordinate, but really we are approaching that y value from the left and right. So we have a hole at 2, 3. So with that, we're approaching y equals 3 from both sides, even though we're not defined there. So the limit as x approaches 2 of f of x is going to be equal to that y value of 3, where we have that hole coming through. Then the limit as x approaches 3, so we have a hole here. The hole is occurring at 3, 2, but then we do have a defined coordinate at 3, 2.5, but that defined point isn't connected to our graph. Again, it's all about what we're approaching from the left and right. So we're approaching that y value of 2. So that would be the limit, not the 2.5. Now, if we're at x approaching 4, and this idea of approaching from the left and right, so we have this jump here, because we have that hole up at let's just say 3.5 for simplicity, and then we have a hole down at 1. So with this jump here, if I think about kind of zooming in, so if I'm approaching from the left, those y values are getting closer and closer and closer to what, that 3.5-ish. If I approach from the right, those y values, those are staying at y equals 1. So what we're having is this, it's not matching up. We're getting this approaching from the left and the right. It's not lining up. And when they don't line up, the limit does not exist. At least this two-sided limit does not exist. When we talk about one-sided limits, we have a left-sided limit, we have a right-sided limit, but we do not have a two-sided limit. So this limit as x approaches 4 for f of x, we'll write DNE for does not exist. So that's how we can evaluate it graphically, just looking at those points and thinking about those y values that we're approaching from both sides. And if they don't match up, then that limit does not exist. All right, our last example here is to evaluate these, and what we can do is use a table of values. So I'll go and show kind of more examples with Desmos and how we can do this. So we have two limits that we're evaluating here. Let me get my Desmos graphing calculator. And what we're going to do is I'm going to adjust my table. So I'm going to leave x for, actually I'm going to clear out, no, I'm starting fresh. Okay, new table. So add item, table, where it says x1, I'm just going to edit that to be x. And then for y1, what we're looking at is the limit as x approaches 0 of 2x squared minus 2x minus 1 over x minus 1. So what we could do is separate up our fraction in the numerator, 2x squared minus x minus 1 over x minus 1. Now, if I want to evaluate the limit as x is approaching 0, what I want to have is a table that's looking as we're getting closer and closer to 0. So maybe I'll put 0 in the middle there. And then I just want to think about what's super close on the left-hand side. So let's go like negative 0.999, negative 0.99, negative 0.9. We could do something like that. And then what's just above, so positive 0.001, 0.01, 0.1, something like that, where we just want to see what are we getting closer and closer to on both sides. So with that, and I'm going to show you there is another way to do this one, but this is just good practice. So I have my x value and y value plugged into the table. So I'm going to go negative 0.9, negative 0.99, negative 0.999, 0, 0.001, 0.01, 0.1. Okay, so from the table, we have this negative 0.8, negative 0.98, negative 0.998. And what we could see, And it doesn't line up, and that's because I apparently just didn't wake up enough. I'm going to leave that in there. Sorry. That's not how 0 works. I want, instead of those 0.9s, negative 0.001, negative 0.01, negative 0.1. There we go. That should be nice and close. Got all mixed up there. But I'll leave it in, because it's probably one of those mistakes that often happen. Okay, 0.01, negative 0.1. There we go. So now we can see our y values really approaching 1 from the left-hand side and the right-hand side. And then we're even actually defined at x equals 0. So with that, we really do just have this coordinate 0, 1. So that limit is going to be that y coordinate positive 1. So how we could have actually done this without a table of values is using something called direct substitution, which is the idea of taking, if x is approaching 0, just let x equal 0 and plug it into the function. So like 2 times 0 squared minus 0 minus 1 over 0 minus 1. And what we would end up with there is what, negative 1 over negative 1, which is positive 1. So we could have done this with just direct substitution. We didn't actually need a table of values because we're actually defined at that point. But let's look at what if I changed the limit so that now we're approaching 1. Well, if I try direct substitution here, I'm going to end up with an issue in that denominator because we'd get a denominator of 0, so it would be undefined. So this would be a case where a hole is coming through in our graph. So this, I would absolutely need a table of values, or at least to look at the graph and see what's happening as we're getting closer and closer to 1. So what I'm going to do is use the same table that I have. I'm just going to change my x values. So I want to look at what's happening close to 1. Let's see if I can do this right. This time I'll have a 0.999, 0.99, 0.9. So things just to the left of 1, and then just above would be 1.001, 1.01, 1. Okay, so I'm going to go back to my table, and the function didn't change at all. All I'm changing is the y values. So I'm just going to go 0.9, 0.99, 0.999. And then we could actually see what's happening at 1, and as you'll see, it's undefined. And then we'll do a 1.001, 1.01, and a 1.1. All right, so coming from the left-hand side, we're seeing 2.8, 2.98, 2.998, so that's getting really close to 3. And I also want to evaluate from the right-hand side, so we're going 3.2, 3.02, 3.002. So from both sides, we're approaching 3. So with that, the limit is going to be equal to 3 as we approach that from the left and right.